Right. So now let's briefly talk about again in detail what actually happens during the hydration process. So as we discussed before, the moment the cement particle comes in contact with water, the hydration process starts, and initially you will have a very rapid heat evolution, and then there will be a dormant period. Okay, that helps us in mixing the concrete and placing the concrete, and then you have initial setting time, initial setting. Then there is an acceleration phase like the one that you see here, and then there is a final setting. Then the heat evaluation reduces like this, and then the rate of heat evolution is more or less is going to be very low. It's not going to increase. Okay, so you have the rapid heat evolution phase, and then you have a dormant phase, and then you have an acceleration phase, and then deceleration phase, and so on. So we have multiple phases at the moment the hydration starts. So that has significance as well. Okay, and as we explained, the products of cement hydration are actually larger than the reactants themselves. So the reactants are your C3S, C2S, C3A, and C4AF, and so on, right? So the hydrated cement grain is going to have larger volume than the dry cement. So that is what you see here. So the degree of hydration here is shown in the y-axis, and with respect to time is shown in the x-axis. So this basically here, the light blue color product is basically your cement. And you see here, before it comes in contact with water, they are separated. The moment you start adding water, then slowly you start forming your calcium silicate hydrate products. Then as the time evolves, you can see that the distance between this particle is going to come, is going to less, and then more and more you see the black color basically indicates the hydration products, and you can see that the size of the cement grain is going to become smaller and smaller because as you are getting more and more hydration products. Now this the particle when they touch each other, that is the thing that we say that as a basically your so you can see here both of them they start touching each other. That's what we call that as an initial set. Okay, and then when they start merging together, that is the time that we say that you have complete setting is kicking in, right? Right. So in terms of concrete state also, this is very important for us because for the initial stage, right after mixing it with water, we want that concrete to be plastic and workable. Okay. It should give sufficient amount of time for us to mix and place the concrete where we want. Right. So that is very important. It should not set very quickly also. That's why the initial setting period is important. At the same time, for removal of formwork and for gaining its strength properties, the final set is also important. It cannot be also too long also. So you can see here from in this period from 2 to about 10 hours, there's going to be a rapid strength development. So your strength as well as the elastic modulus of concrete is going to increase rapidly. And then after this 10 hours, basically you're going to have a continuous strength development. So that is what it is shown here. And this is the way the mechanism is. So now let's look at what are the primary reactions. Okay. So again, tricalcium silicate, it reacts with water and it produces calcium silicate hydrate. And in addition to that, you can see that calcium hydroxide is also produced. So again, from mineral admixtures point of view, this is the calcium hydroxide that will be used and it will react with the reactive silica that is present in your supplementary cementitious material to produce additional calcium silicate hydrates, right? So in addition, so for example, again C2S again is going to react with water to again produce calcium silicate hydrate and then calcium hydroxide. So you hear C3S produces 3 times calcium hydroxide than C2S. So, in fact, if you look at C3S produces more calcium hydroxide than C2S. Okay. Now, what is the significance? This is what we want more. The calcium silicate hydrates are very strong and dense hydration products. That is what it is imparting strength and mechanical properties to the concrete. However, the calcium hydroxide is weak and soluble, right? So we have to be careful. So we need to produce more CSH and less calcium hydroxide, right? And also C3S produces, if you see here, it produces more heat and 3 times the calcium hydroxide than C2S. So that is what, if you look at it, that rate of reaction, C3S and C3A reacts faster, right? So initially that means C3S is going to produce more heat, but at the same time it is also going to produce more calcium hydroxide than dicalcium silicate, which is C2S. Right. So, so now these are the primary reactions. In addition to that, we also have other components, as we have explained in the previous slide. So you have tricalcium aluminate, right? So the tricalcium aluminate, it's going to react with gypsum and water to produce something called ettringite. Okay. So ettringite, again, the chemical formula is given here: CaOl2O3, SO3, and water. And this ettringite is actually a crystalline and needle-like structure. So what you see here, these are like all this needle type of structures is shown here. When this ettringite is formed at the initial stage, okay, there is no problem. Okay, it's a needle-like structure because the concrete is still plastic. It can accommodate when this needle is forming, the volume is going to increase, and that it can accommodate all this thing. However, what happens is all the ettringite is not fully formed because when the heat is released during this initial reaction, it delays the formation of this ettringite. Okay, so what happens is this again, this ettringite and tricalcium aluminate and water, they combine together, they form calcium monosulfoaluminate, which is a more stable product under high heat. Okay, so the high early heat basically delays the formation of not all the ettringite is formed. So the ettringite again, it reacts with tricalcium aluminate and water, and it forms a more stable calcium monosulfoaluminate product. Okay, but the issue is when additional sulfate and water is available, this calcium monosulfoaluminate can react with additional sulfates and water, and again it can convert it into ettringite. So that is what we call that as a delayed ettringite formation. When the concrete is actually hardened, when this kind of needle-like structure forms, when your external sulfate and moisture is available, what will happen is you form this kind of a ring type of cracks, that what you see here. Okay, all this kind of cracks are formed. Okay, so this creates a lot of durability issues. Again, you can see here all these cracks. Okay, so this is because of delayed ettringite formation. So one way to reduce this delayed ettringite formations, of course, we have to prevent it, uh, that external ingress of your sulfate, or another way is to reduce this tricalcium aluminate. So that is what people in sulfate resisting cement, that's what we saw, that C3A content has to be less than a certain percentage. So that is the way we can reduce this delayed ettringite formation. Okay, so again, as I've explained, so this monosulfoaluminate can again convert into ettringite when moisture and additional sulfate is available. So this is what it is called as delayed ettringite formation. Why all the ettringite cannot be formed at the initial stage? Because of this high early heat, which will prevent formation of all the ettringite, and it will form a more stable calcium monosulfoaluminate at the initial stage. Then when more moisture and sulfate is available, then you form this delayed ettringite, which is going to create a cracking, this kind of rim kind of cracking around this aggregates, and which is not good for concrete, and it is going to create a lot of durability issues. Right. Now let's get into the mechanical properties. So as a structural engineer, usually we are more concerned about how the sustained behavior of concrete is going to be under compression, tension, and so on. We want these properties to be used for a design. Okay, so ideally for a design, we need to get complete stress strain curves. Okay, but for every project, we cannot go ahead and test and develop this stress strain curves. So people have already done a lot of testing, and they give you some simplified formula based on certain minimum values. One of the values basically compressive strength. So if you give compressive strength of concrete, we have models that are available that will give you what would be the stress strain curve, okay, depending upon what range that you do. So mainly we are interested in F prime C, and for deflection calculations and for other calculations, we also need what is the elastic modulus of the concrete. And also, concrete is a brittle material. So we want to know exactly at what strain levels it is going to give away. So that is also we need to careful. In addition to that, for flexure and especially for pre-stressing application and all, we need to know what is the tensile strength, okay, of concrete. Again, concrete tensile strength can be measured through multiple ways. You can do a direct tension test, which is actually difficult, or we can do a bending test and get bending tensile strength, or we can do a something called Brazilian tension test, or it's called a splitting tension test. We will talk about that. For compression, usually we test, if you want the accurate actual material properties, you need to test cylinder with an aspect ratio of 2, right, to get the actual sustained curve of concrete. And for design purposes, we usually use 28-day strength. And in India, the standard is actually to test cubes of 150 size and a uniaxial compression, because it's easy to cast and test a cube. So that is why our code has adopted cubes for testing and finding compressive strength. But if you look at the American code, it suggests you to test cylinder to get the actual stress strain curve. And this is the way the failure is going to be for cylinder and cube. So now the reason is why the cylinder gives you the actual representation of the material properties is basically, so if you look at cylinder, right, and you subject it to, let's say, right. So we are here talking about length basically equal to 2 times the diameter of the cylinder. So if you go, you know that Saint Venant effect. To get the actual uniform distribution, at least we need to move away by the least lateral dimension. So if I am testing a cylinder with an aspect ratio of 2, and if I go away by a distance of d, then you get at least one cross section which is having constant normal stress, which is free from boundary condition effects. So that is the reason it's better to test specimens of aspect ratio 2 to get normal uniform stress distribution, which will lead to actual failure condition. So when you test cylinder, that's what, this usually you have this kind of uh, cracking that is going to come, and it will have two types of cones that will be formed like this. Okay, we will talk about the failure mechanism of concrete in the coming slides. uh, but the test that you do for cylinder, and usually we call this strength as F prime C, and that is actually 80% of your cube strength. Again, why the cube is giving higher strength? There's going to be a lateral confinement. So when I'm testing a cube, and let's say that this is my, the plate end. Okay, plate end is basically from the machine, compression testing machine. Let's say this is a stiff plate end. Okay, so this is your plate end, and this is your cube. Okay, now when you apply compression, of course, there's going to be a lot of friction. Okay, at this interface, right, between the plate end and the cube. So when you squeeze the concrete in compression, it wants to expand in the lateral direction. So it's going to be wanting to expand like this, right? Though you're applying compression like this because of Poisson's effect, right? However, at the end surfaces in the cubes, there is going to be a lot of friction between the plate and the cube, right? That is going to prevent this lateral expansion, and it is going to put it in some form of lateral confinement. So what will happen is, so the cube is tend to give you higher strength than your actual material property that you will get only when you test with specimens of aspect ratio of 2 or more. Okay, so that is why the cylinder is usually gives only 80 percentage of your cube strength, or your cube strength is actually 25 percentage higher than your actual material property. Okay, actual compressive strength. Okay, so this comes from cube, because 150 by 150, first of all, we don't get this uniform stress distribution, because by the time I go to D, then I reach the bottom plate. Again, that is that where we are applying the load. So because of this, we need to, actual material property is basically 80 percentage of your cube strength. Right. So let's say that we are testing some concretes of different grades. Okay. So what we are seeing here is, let's say I have taken a cylinder. Let's say this, I'm applying a compression force like this. Okay. And I put some LVDTs. Okay. LVDTs are nothing but linear variable displacement transducer. These are sensors that gives me the deformation between these 2 points. Okay. So continuously I keep increasing the load, and then I keep measuring how much these 2 points are moving towards, because you're applying compression, these points are going to move towards each other. So that is your strain. And you know the definition of strain, epsilon C is nothing but, if you know the deformation between 2 points, and if you know your original length, which is gauge length, then you can get your strain epsilon C. And if I know my load, then my stress sigma can be written as, or in other words, let me write FC. So FC can be written as P divided by area, where area is basically cross-section area of your cylinder. So in this way, I can get for any load application what is stress, and if I measure this delta, and if I know the gauge length, I can also get my strain epsilon C at any point of time, right? So let's see that. So I do this exercise, and then I get I test concretes of different grade. Let's see how the stress strain curve behavior is going to be looking like. Now this is the way it is going to be for a 20 megapascal concrete. So this is cylinder, so that is going to give you the actual compressive strength. So if you see here, this is my strength, 20 megapascal, and roughly it reaches a peak strain of at about 0.002, and it is going to go. So if you look at it, so this is the way it is going to be for your 20 megapascal concrete. So as I go higher and higher, let's say now let's look at 30 megapascal. So what you see here is, of course, the elastic modulus, which is basically the initial slope. The elastic modulus is increasing and strength is increasing. And you also see here the strain corresponding to peak. Okay, that is also increasing. Now let's look at the next one, 40 megapascal, close to 40 megapascal. Again, same, elastic modulus is increasing, strength is increasing. As the strength is increasing, elastic modulus is increasing. Now the strain corresponding to peak is also increasing, right? And if you go to 45, again same trend. And if you go to 60, again same trend. And then if you go to 70, again same. So you can see that with the increase in compressive strength, elastic modulus is increasing, and the strain corresponding to peak stress is also increasing. So that is what this dotted line, okay, the dotted line keeps shifting towards right. So that indicates that the strain corresponding to your peak is increasing, right? Okay, so this is the way it is. So what, and another thing what we can say is, we can also conclude what is your failure strain. So this is strain corresponding to peak. The failure strain, which we call that as epsilon Cu, can be defined when your strength, let's say, decreases by 20%, or the peak strength, when peak strength decreases by, let's say, F prime C, if it is decreasing by more than 20 percentage, at that point we call that as a failure. Okay, so I can define failure in multiple ways. Usually when the strength decreases by more than 20 percentage, we can term that as failure. So similarly, if you go back and look at what is a failure strain, so that is what we're going to look at it. So this is my failure strain for the 20 megapascal concrete. For this 80 megapascal concrete, this is my failure strain. Okay, so what can we infer from this? If the concrete strength is lower, my failure strain in this case is about 0.004. But for a concrete strength of about 85 megapascal, my failure strain is about 0.0035 or so, right? So we can infer that the peak strain is increasing with increase in strength of concrete. However, the failure strain, which we call that as epsilon Cu, and peak strain is basically we write that as epsilon prime C, which is peak strain. Okay, okay. This is your ultimate or failure strain. Okay, this is your ultimate or failure strain. So we can infer that epsilon prime C is increasing with increase in concrete strength. However, the epsilon Cu is reducing. Okay, so these are the important observation that we need to keep in mind, especially when we are using high strength concrete. The reason is there is something called post peak ductility of the material that is usually measured as the difference between the failure strain and the strain corresponding to your peak strain. So what can we infer here? If you see this case, for the first case, for the low strength concrete, the difference between epsilon Cu minus epsilon prime C is actually larger. However, if you go for 85 megapascal concrete, the red color one that we are seeing here, the difference between epsilon, so this is higher, okay, for F prime C, right? So for an F prime C, this is for 20 megapascal, it is lower. For let's say 80 megapascal, this is less epsilon Cu minus epsilon prime C is actually lesser for 80 megapascal. This is for 20 megapascal. This is for 80 megapascal. So we can clearly see that the ability of the material or the ductility of the material is going to reduce as the strength of the concrete is increasing, right? So maybe I'll erase this. So what are the things that we can conclude from here? Because these are important, because more and more we are using this high strength concrete. It's important to understand the consequence of using high strength concrete. So as we have seen, when the concrete strength is increasing, the peak strain is increasing. When the concrete strength is increasing, epsilon ultimate is decreasing. For example, that's what we saw. 20 megapascal, it's 0.004, and for 80 megapascal, it is 0.0035, right? So the epsilon ultimate is, so as the strength of the concrete is increasing, the ductility is raising. Again, ductility, how are we measuring in a it is the difference between epsilon ultimate minus epsilon peak. Actually, concrete, no, ductility is usually associated with yielding of steel, but here we are talking in terms of post peak ductility from concrete point of view. There is no yielding. We are measuring ductility in terms of the difference between ultimate strain and peak strain. So if you see that increase in concrete strength reduces the ductility or the ability of the material to hold for a large strain. So this is a video of concrete that I tested. So what you see here is the left one is a normal strength concrete, okay, and you can see here for normal strength concrete, the failure progression is gradual, okay. And if you see high strength concrete, okay, this is about 30 megapascal concrete which was tested, and this is about 100 megapascal concrete, okay. So what happens here is in 100 megapascal concrete, you can see that there is a complete disintegration and there is a complete crushing that is available, and it is happening in a very rapid fashion. So that's why from the last slide also we have seen that as you go higher and higher in strength, your post peak ductility is going to reduce. So that's what it's happening in high strength concrete. For example, the one that we are seeing here in this video for 100 megapascal, the moment it reaches peak strain, quickly it is also reaching your epsilon Cu. So the difference between epsilon Cu and epsilon prime C is getting lesser and lesser as the strength of the concrete is getting higher and higher. So this is one important aspect that we need to keep in mind. So if you're going for high strength concrete, it is always better to put some fibers that will give you a little bit of ductility. Again, that fiber dosage also is very, you have to design for it. Right. So now let's look at what are the stress strain behavior of constituents of this concrete. We have explained that concrete has cement, water, and aggregates, coarse aggregate and fine aggregate. They're all combined together along with some mineral admixtures also if required. So if you look at only the stress strain curve characteristics of hardened cement paste that includes cement, water, and fine aggregate, and the coarse aggregate, and we see that for a normal strength concrete, usually the hardened cement paste is less stiff and less stronger or weaker than your coarse aggregate, because the aggregates are going to be stiffer and stronger than your hardened cement paste. And from basic rule of mixture, concrete is composition of the concrete is basically composes of coarse aggregate plus hardened cement paste. So its properties as a composite, it's going to be somewhere in between that of your two constituents, two major constituents, which is nothing but your hardened cement paste and coarse aggregate. One important thing to note here in normal strength concrete is because the aggregates are stronger here for a normal strength concrete, usually we say when it is less than 40 to 50 megapascal concrete. Okay, so for such kind of materials, your aggregates are stronger and stiffer. So when it is undergoing compression, the cracks actually originate at the interface of the cement paste and your aggregate, and then it goes around the aggregate. So, however, in high strength concrete, now you're using lower water cement ratio and you're packing that cement paste with all fine particles. So what happens? It will become reverse. The hardened cement paste will become stronger and stiffer than that of aggregate. So when you subject it to compression, what will happen is when the crack is forming, it can cut through the aggregate. So that is why you get a very brittle form of failure. That's what we saw in the last video as well. Okay, so aggregates are having high stiffness, and hardened cement paste usually have low stiffness. This is applicable for normal strength concrete. Okay, and for high strength concrete, it is going to be changing. Okay, it is going to reverse, and the hardened cement paste will get closer to the aggregate, or even it may be higher than that of your aggregate. Okay, so this is what it happens. Now let's look at it. Now when I do this testing of a cylinder, okay, I'm not only interested in compression, I'm also going to see what is going to happen on the lateral strain, okay, and I'm also, if I know the longitudinal strain and lateral strain, I can also calculate volumetric strain, okay. So let's look at what happens when this cylinder is tested in compression. So as you can see, epsilon 1 is your longitudinal strain. The same way, we can also measure what is happening in the lateral direction, which is your lateral strain, epsilon 3. And your volumetric strain is basically epsilon 1 plus 2 times epsilon 3. And you have, this is the way the stress strain curve is going to behave, right? So we have seen it in the previous slides also. So you get this nice parabolic stress strain curve, and then you're going to have post peak behavior. So, right, so this is the way, if you plot your here what we are plotting is stress is again the sigma 1 versus epsilon 3, sorry, epsilon 1, which is your longitudinal strain. So this is the way it is going, because this is undergoing compression, right? So it is there. Now when you plot the same thing, stress versus your lateral strain, and you know that there is a Poisson's effect is going to be there. When I squeeze the material in compression, in the lateral direction, it is going to be in tension, right? So that's how this is going to be, and it is going to keep increasing, and then it will become non-linear at certain point of time. So that is what we are seeing here. So it is going to become non-linear at this point, and then it is going to increase quite dramatically, this epsilon 3. Now, what will be the volumetric strain? Volumetric strain is basically how the volume is changing. Okay, though I am testing in compression, of course, initially it will all be volumetric strain also will be in compression. Okay, that's what you see here. Up to here, there is going to be compressive strain, the volumetric strain, and we measure volumetric strain plus epsilon 1 plus 2 times epsilon 3. Right, so this is the way we measure your volumetric strain. Then after a certain point of time, again you see here the compressive strain will change into tension because the concrete is going to start dilating. Now let's see what exactly it happens. Okay, so if I take a small element within this cylinder and I look at it, so what will happen is initially as I apply more and more compression, there will not be any crack. Okay, and everything will deform, and you measure your epsilon 1, but usually up to about one third of your compressive strength, there will not be any cracking. And we are talking about normal strength concrete, less than, let's say, less than 50 megapascal concrete, right? So as I apply more stress, more than, let's say, 30% of your compressive strength of concrete, then what will happen is for a normal strength concrete, we know that you're going to have basically the interface between the aggregate and the cement paste is going to be weaker. So you will start developing this called bond cracks. So these are called as bond cracks. Okay, these bond cracks will develop at the interface between the aggregate and the cement paste. As I apply more and more load, okay, then what will happen is these bond cracks will start joining together. So that's what we say. Usually about 45 to 50%. We call this region as your stable crack initiation region. Sorry, stable crack initiation. All these bond cracks form. Then in the next stage, which is this, what will happen here is all the stable, these bond cracks will start connecting together. As I apply more and more stress, again, why is that it is forming only at the interface? Again, there is something called interfacial transition shown between the aggregate and the cement paste. Usually that ITZ is a weaker zone. So at the weaker interface, you are going to develop these bond cracks, and the bond cracks will start joining together in the next stage. Usually that happens after 40% of 40 to 60, 70% of your compressive strength when the stress levels are there. But then what will happen? You will also have cracks that are happening in the mortar, which is in the cement paste itself. Then those mortar cracks also will start joining together with this bond cracks. Then you reach something called as a critical stress level, which is very, very important from behavior point of view. So once this critical stress level is reached, what will happen is the material will start dilating. So that means the volume is going to expand. Okay, though we are applying compression, so the volumetric strain is going to increase. Okay, not is going to compression, it is going to expand. So that is why there is going to be, after this critical stress limit, the volumetric strain changes from compression to tension like this. Okay, so this establishing this critical stress level, usually it happens about 90 to 90% of your compressive strength. After that, it reaches a critical stress level, and then you'll have unstable crack propagation, and then you will have this kind of post peak behavior. So if you do not have any fibers or any other reinforcement, then you cannot contain the crack propagation, and it will reach its unstable crack propagation and lead to complete failure. So this is very important. Again, from confinement point of view, from column confinement point of view, this reaching this critical stress level is important. Okay, so this is the way the failure happens. So initially there are no cracks, then the bond cracks forms, and then the bond crack starts connecting together. Then you also have mortar cracks forming, then bond cracks and mortar cracks combinedly connecting together, and it reaches the level of critical stress. Then there's going to be a lot of dilation that is happening in the concrete, and it will lead to complete failure. So this is how the failure mechanism happens in compression.